Any patterns that they identified? Some things you kind of saw as you built up your star? Yeah, Benson.
Usually it was all just like simple math, like just addition, subtraction, and multiplication.
Yeah, right, very simple math, right? It's like, okay, 1 plus 1 makes 2, so on and so forth, right? Good. How's my face bet? Any other observation of patterns that we saw? Yeah.
The masses, like something had a mass, they just added together and did a final number.
Yeah, so they would just combine together into one big one, right? Good. How's my face bet? Yeah, Rachel.
Normally what you can do is you can just find the same element and then just add like one thing to create the other one. So like simple, like you just use the same element, just add a couple things and then
Very good. So there's kind of a stepwise thing, right? Where the answer to the question above was often what was used to start the next one. This is literally the process of a star, and it is known as fusion. Now, just a reminder, so this is your Unit 1 note packet. We're not going through this entire thing today, by the way. Did you not get any? They're not passing that. But yeah, so this is your Unit 1 note packet. Remember, there are blanks and stuff to fill in, but then these are your notes. So add to them, write whatever you want, highlight. We're not turning these in, but they should be a very good resource for you to use. Okay? So fusion is this process, and literally just think of the word fuse, of things coming together. So fusion is literally when two atoms join into one bigger atom. Once again, fusion, fusing. Okay? Fusion, once again, is what happens in the stars. Okay? Now this process, and I apologize, I can't turn these lights off anymore. They did something to them over the summer. So hopefully that's not too bad for in the back. Can you see that okay still? Okay. So we call the things that start as the parent nuclei, and then they fuse together and make what's known as the daughter nuclei. There's just kind of some terminology that we'll use. Now, it's a simple process, and like a lot of people notice with the pattern, it's very simple math. In theory, though, it's not as easy as just like, okay, here, I have an atom, you have an atom, let's throw them together and hope they stick. Okay? The energy that is needed to make fusion happen is 72 million degrees Fahrenheit. You need this is even more than extreme, but extreme amount of heat to make fusion happen. Now, to give you, it's not totally real, but it has a little basis behind it. How many of you have seen, original Spider-Man series, number 2 with Doc Ock? Have you seen that one, some of you?
Yeah.
So in that movie, he's literally trying to create fusion on Earth, because he creates like a miniature sun. Once again, it's something actually scientists are trying to do, but you can imagine how tricky it is to manage that temperature on Earth, right? And stuff not just completely fall apart on us. With this process, what's cool though is not only does it take a lot of energy for it to happen, once it does happen, it actually releases even more. So the heat and light that we see from the sun is because of the fusion process that is constantly happening within it. It releases this energy, which you saw in your equations, and that amount of energy is crazy. And we'll do a little demonstration visual at the end to kind of show how much that is. So, by the way, if I ever move on in a slide and you need me to go back, just let me know. Is everyone okay if I go on to the next one? Okay. Okay, so like I said, the sun is actually doing this process right now. It's fusing hydrogen into helium. Okay, look at your little map and then look at the periodic table. Okay, so hydrogen is the very first element, the simplest there is, right? It has one proton. Hydrogen can fuse into helium, which it did here in the first reaction. Helium can then fuse into carbon, right? And then it just kind of continues. Carbon can fuse into magnesium. What's the last one that got built inside the star? Where did your process end? Iron. Okay? Iron is the last element that is formed through this process of fusion. Flip your pink paper over to the back and you'll see a little picture of a bunch of different rings. Okay? okay? A star, in a sense, kind of forms like an onion, okay, where you'll have this hydrogen layer. The hydrogen layer then fuses into helium, so on and so forth, and they build and build and build and build. It gets to a problem when we get to iron. Does anyone know, because you're in astronomy or something, what happens to a star after it makes iron? Any guesses? Tanner? Supernova. Yep. So iron is too heavy of an element for the star to fuse anymore. And so what happens is the core collapses. It collapses, it explodes, and then because the explosion is so massive with so much energy, all the rest of the elements up to 92 are created. So hydrogen through iron are made in the star, and then cobalt to uranium are made in the supernova explosion. All the ones that come after uranium, and we'll talk more about this another day, but all these ones that are white, these are actually man-made elements. They aren't created in the stars, they've been made in a lab. It's, once again, not totally real, but there's parts to it. In Iron Man 2, he creates a new element. Vibranium, right? No, not vibranium. What does he make?
He makes something for the arc reactor.
Anyways, he makes a new element, right? That can be done on Earth. All of these were made on Earth. Yeah, Jeremy. Oh, right on the line. It says fusion reactions generate the heat and light that come from a star. So those are the two blanks right there, heat and light. So with this idea of the elements, I'm just going to go to our picture here. This is why that the majority of the universe is just hydrogen. Because it is the simplest Lego that makes up all the other Legos that we have, right? Helium is the next abundant, and then in comparison, all the others are very, 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 very small in comparison. Because once again, they're all made from that beginning one. Now, despite what you believe, this is the idea of the Big Bang. The Big Bang is the idea that it started with one, and they built and built and built, and then everything else, all the other elements, came from it. Now, you can have your own beliefs on the Big Bang, of course, but you can't deny the fact that elements are created in the stars through this process. That is the scientific fact, that elements are created this way. Which is pretty crazy to think that that's where they all come from. There's a really cool poem, if you want to look it up, called Stardust. And it talks about that pretty much we're all made from stars. But it's kind of a cool little poem. I should have pulled it up, but I just thought of it right now. Okay, questions on fusion. Okay, so here's my analogy for fusion with the Legos, okay? Fusion is taking a red Lego and a red Lego, melting them together to create a new green Lego. Now the reason why I changed the color is why? Yeah, it's a new element, right? It's not the same thing. It's not just a bigger hydrogen. It's actually a brand new thing that can be totally different from the rest. Okay? All right, we're going to talk about the reverse process, okay? So the reverse of fusion is a process known as fission. Okay? So if fusion is coming together, fission is splitting apart, right? So fusion is the process of taking an atom and it breaking into two or more smaller atoms. Now, fusion, like I said, naturally happens in the universe in the stars. Fission is what happens inside of atomic bombs. Okay? This is not something that happens spontaneously. Scientists found a way to encourage the atom to split. It's probably a good thing it doesn't just happen on its own, right? That would probably be problematic for all of us, okay? So, nuclear fission involves splitting a large, heavy nucleus into two or more smaller nuclei. Neutrons are always involved in the process. And after you get these filled in, I'll kind of show you an example. Okay? The neutron is what acts as the little knife to cut the atom. Okay? So they have an atom, and once again, it's normally a big one. It's really hard to do fission with something that's small, right? Kind of the same idea. It's hard to cut something that's small into smaller things. So we kind of have to have something that is large. They shoot a neutron at this atom, and that neutron causes it to split. In that process of it splitting, some random pieces get thrown off, like more neutrons, and as well as energy. And we'll talk about where this energy comes from here in a second. But it is a chain reaction that causes it to keep going. Those neutrons then run into other neutrons, or other atoms, causing them to split, and the process continues. I'll get those blanks in, then I'll show you this picture here. So when we talk about the strength of nuclear power, which we'll talk about a lot in this class, it's not coming from a single atom per se, right? One atom isn't what causes a mushroom cloud. It's that one atom splits causing others to split, others to split, others to split. Domino effect of energy is what we get here. Let me see my picture. Here we go, right? So here's the idea. So this one gets split, shoots out more neutrons. Those hit these ones, those split. Continue, continue, continue to all that energy. Okay? Now, the energy idea comes from this component of there's a critical mass. Okay, the critical mass is the minimum mass required to sustain a chain reaction. It's kind of the idea of, like, think of with dominoes, right? If you were to set up dominoes, if you set them a little too far away from each other, it gets very disappointing because it just stops. That's kind of the idea of this critical mass. If you don't have enough, then the dominoes can't hit the next one and it stops it in the end. So that's something that they calculate when they are trying to produce energy from fission. Is everyone okay? All right, mass defect. So scientists back in the early 1900s found an interesting thing with atoms. This is where they were learning about the protons and neutrons and all those things. And they found out that if you were to add up 2 protons and 2 neutrons separately, together it would have a mass of this. But then when they came together to make helium, the mass went down. So it was a really kind of confusing thing because it's like, shouldn't it be the same? Like, why did it go down just because they came together? And we know that matter can be created or destroyed, so they knew that it had to be changing into something, and this is the problem known as the mass defect, where they found that some of the mass of the separate components was used to make this thing known as the binding energy. The way I think about it, it is the glue of the atom. Okay? So the binding energy is the glue that holds the atom together, and that was the missing mass. So some of the mass from the individual pieces got converted into energy, didn't get destroyed, but it got converted to hold the atom together. And this is known as the nuclear binding energy. And the more energy it has, the more stable the nucleus will be. And this is actually what goes into the very famous equation that maybe your whole life you've wondered what it's all about, of E equals mc squared. Einstein's very famous equation is all about this component of mass defect. Now, we're not going to calculate with this or anything like that, but it helps us understand what mass defect is. So m is mass in this equation. C is the speed of light. Which is always a set constant value. Once again, you don't need to know this, but to show the point here, this value of the speed of light is 3.0 times 10 to the 8th meters per second. Okay? So is this number a big number or a little number?
Pretty giant.
Very big. So in this equation, we are squaring this number. So even if m is really, really small, E is the energy that comes out is tremendous from it. And that's, once again, where we get all this energy from. Number one, the sun, why the sun has so much energy. And second, why nuclear bombs and nuclear power have so much energy. Okay? So nuclear binding energy is the energy that gets released when the nucleus is formed by the protons and the neutrons. The E, once again, represents the binding energy. And if we were to separate them, then that energy gets released. The big takeaway is this. Put a star next to this sentence. The higher the binding energy, the more stable the nucleus will be. Once again, because the binding energy is the glue. Right? So the more glue an atom has, the more stable it's going to be. Which means it's less likely to be broken up.
Where you say that word?
Yeah, so the higher the binding energy, the more stable the nucleus, because it holds the atom together. Okay. All right, we're going to do kind of a weird little demonstration, but hopefully it will help sink the point home. Is everyone okay if I cover this up? Okay, so no, not Lehigh 8. Okay, here we are. Okay. Here we are. Right there. Okay. Now, the reason why I picked Skyridge as our location where we're going to drop an atomic bomb is because you'll understand the blast radius. If I just pick some random desert in the middle of nowhere, it's hard to comprehend how big of a space that is. But because you know this area, because you'll probably be like, oh, my house is safe or it's not safe. That's why I picked Lehigh. Okay, but I don't do it in any way. I love our school. I'm not trying to destroy it. It just helps you comprehend it better. Yes.
After we blow up Scarce, can we blow up Lone Peak as well?
Yeah. No, mine as well.
Mine as well.
Why don't we do all the right ones?
Just go in the middle of the three and just see what
Just see what we think goes. Okay, second thing that I just wanted to make sure you understand here. So the point I'm doing here is, so we're going to drop two different types of bombs. Okay, we're going to drop atomic bomb, which is a fission reaction. Now what happens in fission? The splitting. Okay, we're going to see the energy that comes out of that. We are then going to drop a fusion bomb. What happens in fusion? Coming together. Okay, I do this because it, once again, it sticks with you when you start dropping bombs on things. But I don't mean to make light at all of the tragic things in history that have come from nuclear warfare. Because what happened at Hiroshima and Nagasaki is horrible. And if anything, this should show you as well like how devastating nuclear warfare is. So please don't think I'm making fun of it in any way, because I'm not. But I've just found in my years of teaching that doing this students tend to remember it really well. So, okay, here we go. Okay, where's the one we want? Okay, here we go. Okay, so this first one is a fission reaction bomb. Okay? Okay, ready?
I'm safe, baby.
So, here's kind of what our different colors mean. So this is like the outside parameter. So if you can't quite tell, it's going all the way up onto Traverse. Here's Thanksgiving Point over here. Almost to Lone Peak, because Fox Hollow's right there. And then we're down past, where are we at in Lehigh?
I think I'm dead.
Almost to Lehigh High School, right? Because there's the overpass. Okay.
Cemetery?
Oh yeah, cemetery's way gone.
I think I'm in the green zone.
Yeah, I'm
So
dead.
green means that you are struck by radiation, which means you might not die right away, but you'll probably die in a few years. The inner blue ring, this one.
Just like the massive.
So the big outside one. So that's the air blast radius. So that farther outside air blast radius says that glass windows are expected to break. It will cause many injuries to the surrounding population. And then anything within this orange one, everyone in that radius is going to get 3rd-degree burns. So,
I can live with that.
okay. So, pretty extensive, right? Of an area.
I don't know.
Okay. Okay, so now this is a fusion one to compare the difference of energy, okay? All right, ready?
Yeah!
Just a little bit. I think we got a lot of other people too. So in case you can't read, okay, this is Provo, okay, and we're all the way up to Taylorsville.
Wow.
So which one has more energy, fission or fusion? Fusion. Way more energy, right? So, okay, questions on either of those? Okay, we'll talk more about their energy. Now, obviously, this is a very negative side of their energy. We'll have a whole unit where we'll talk about the positive sides of how we could actually harness this energy and use it to like power entire states. That's kind of a cool thing, but it's kind of for another unit. So just so you know, so the 2 bombs that have ever been used, so there's only been 2 bombs that have ever been used in war, right? The U.S. did it in World War II. Outside of that, all these other ones have just been created and tested, but they've never been used on people. Okay, any questions? Okay, so we'll kind of keep talking about fission and fusion. That's kind of our theme as we go throughout. One of the biggest things is these 2 types of reactions are known as nuclear reactions. Nuclear because they deal with the inner part of the atom known as the nucleus, which is what we'll kind of dive into next time. Okay? All right, you got 7 minutes to finish up the back side of your activity page. And then if you get that done, then you can start studying for elements quiz number 2. Okay, so your 2 homework assignments are to study and then to upload that on campus. If you haven't got your laptop put away yet, if you will put it away because my next class doesn't need them.